So now we'll consider the case lambda equals 0. Here the ODE is f double prime plus f equals 0. And of course the general solution to that is f of x equals c1 cosine of x plus c2 sine of x. We check the boundary conditions as before. We want 0 to be equal to f of 0, which again is c1. And we want 0 to be equal to f of pi, which now has to be c2 times sine of pi. Now we note that, of course, sine of pi is equal to 0, so no matter what c2 is, we'll meet the second boundary condition. So as long as c1 is equal to 0, then we can always solve both the ODE and both boundary conditions. Namely, the solution would have to be a scalar multiple of what I'll call f1 of x is sine of x. So it turns out that in the lambda equals 0 case, we do get a non-trivial solution via f1 of x equals sine of x. And now case 3, we'll take lambda equal to alpha squared for some alpha greater than 0. And then the ODE is f double prime plus f equals alpha squared f. And that rearranges to f double prime plus 1 minus alpha squared f equals 0. Now we will have to consider a few more cases here based on what alpha is as a positive number. So first, what happens if 1 minus alpha squared is less than 0? Then we could just rewrite the ODE as f double prime minus alpha squared minus 1 on f equals 0, where alpha squared minus 1 is positive. So we could solve this ODE with f of x equal to c1 e to the theta x plus c2 e to the minus theta x, where I've abbreviated theta is square root of alpha squared minus 1. And again, that square root is just fine because alpha squared minus 1 is positive. So that's our general solution in this first subcase. What do the boundary conditions force? You want 0 equals f of 0 equals c1 plus c2, and 0 equals f of pi equals c1 e to the theta pi plus c2 e to the minus theta pi. As I always like to do, we'll rewrite this as a linear system. It's the matrix, first row is 1, 1, second row is e to the theta pi, e to the minus theta pi, times the vector c1, c2 equals the 0 vector. Calculate the determinant of this matrix. It's e to the minus theta pi minus e to the theta pi. And that is definitely not 0 because theta is not 0. So the matrix is invertible, c1 equals c2 equals 0, and the only solution is the trivial solution. Case 2, 1 minus alpha squared equals 0. In that case, the ODE reduces to f double prime equals 0, so its solution is f of x equals c1 times x plus c2. We check the boundary conditions. 0 has to be f of 0, which we know is c2, and 0 has to be f of pi, which is c1 times pi, since c2 is 0. So of course that means c1 equals 0, and c2 is 0, and f is trivial. Nothing interesting here. Case 3, 1 minus alpha squared is now positive. Then the ODE is, once again, f double prime plus 1 minus alpha squared f equals 0. And now let's put theta equal to root 1 minus alpha squared. We can take this square root because 1 minus alpha squared is positive. In LaTeX, this is actually a var theta, and I'm using that for variety's sake and because var theta to me looks cool. So what's the solution to our ODE? F of x equals c1 cosine of theta x plus c2 sine of theta x. Check the boundary conditions once again. 0 equals f of 0 equals c1, big surprise. And 0 equals f of pi equals c2 sine of theta pi. So we get a trivial solution if we take c2 equals 0. So let's force sine of theta pi to be 0. That means we want theta to be an integer. So that means we want root 1 minus alpha squared to be equal to k, which is an integer. But root 1 minus alpha squared is going to be a positive number, so k should be a natural number, a positive integer. And we can solve this to say that alpha has to be root 1 minus k squared for k a positive integer. So alpha is positive and k is a positive integer. When can this happen? When can the square root of 1 minus k squared be positive? Well, if k is equal to 0, it happens. But then if k is equal to 1, alpha would be 0. That's not allowed. And if k is equal to 2 or higher, then you start getting to complex numbers. So the only way this can happen is if k is equal to 0, so alpha is equal to 1. But that means that 1 minus alpha squared equals 0, and then we wouldn't have 0 less than 1 minus alpha squared as assumed at the top of the slide. So we get a contradiction, and the only possible course of action is to take C2 equals 0. So yet again, the only solution is trivial. Let's summarize what we did here. We wanted to find all real numbers lambda and all non-trivial functions f that solve the boundary value problem f double prime plus f equals lambda f on the interval 0 to pi, with boundary conditions f of 0 equals f of pi equals 0. This can happen when lambda equals 0 and f is a scalar multiple of sine of x, or if lambda equals 1 minus k squared for k greater than or equal to 2, and f is a multiple of sine of kx. So let's simplify all this by putting lambda k to be 1 minus k squared and phi k of x to be sine of k times x for k greater than or equal to 1. In particular, we see that lambda 1 is equal to 0 and phi 1 is equal to sine of x. Here's what we have shown via our work in this problem. A pair lambda f, where lambda is a scalar and f is a function, solves our boundary value problem with f non-trivial if and only if we have lambda equal to lambda k and f equal to a scalar multiple of phi k for some positive integer k. So this sort of discrete set of choices with a special relation between lambda and f, these completely encapsulate all solutions to the boundary value problem star that are not identically 0. And if we look at how we've written things, or how we could write things, we in fact have lambda k plus 1 strictly less than lambda k. So the lambda k's form a strictly decreasing sequence of real numbers. And in fact, the limit as k goes to infinity of lambda k is equal to minus infinity. Moreover, if we stare a little bit at the functions phi k, we see they're all orthogonal in the L2 inner product. Namely, the integral from 0 to pi of phi k of x times the conjugate of phi j of x is equal to 0 whenever k is not equal to j. And that's just something you grind out with integrals of trig functions. Perhaps even more remarkably, these functions phi k are part of the Fourier sine series for a function on the interval 0 to pi. So these functions phi k sort of form a basis for a rather general function space on the interval 0 to pi in the following sense. Namely, you can write the average of the left and right hand limits, f of x plus f of x minus over 2, for a given piecewise continuous function on the interval 0 to pi, as the following kind of funky sum, the sum from k equals 1 to infinity of the inner product of f with phi k and L2 over the L2 norm squared of phi k times phi k of x. This is just a fancy way of writing a Fourier sine series for f, given that phi k's are all sine of kx's. These properties, the fact that we have a countable discrete set of scalar solutions lambda, the fact that the function solutions phi k are orthogonal when the indices are different, the fact that this special kind of sum represents, at least in an average of left and right hand limit sense, the functions on the interval, These properties are not special to this boundary value problem that we've been studying all along. They are in fact representative of boundary value problems in general, assuming the right hypotheses. And this is what we're going to develop next in a rather more abstract sense.